This is just a short concept video on the concept of solubility. So we can ask ourselves, why do things dissolve? We have this gut instinct that for example, naphthalene won't dissolve in aqueous solution, but sodium chloride will. And we get to those gut responses because of our experience, but can we use thermodynamics to explain actually what's going on? Well, ultimately, everything in physical chemistry happens essentially because of the Gibbs equation. Delta G is equal to delta H minus T delta S. You can use it to explain any process you like. And in this case, I'm going to combine it with the equilibrium Gibbs version as well. So delta G is equal to minus RT log K. So when something dissolves, it's because the process of dissolution has a bigger negative Gibbs energy than the process of breaking that lattice enthalpy. So if I look at kind of just a crude model of sodium chloride, on my left here I have just sodium chloride in its crystal. It's a low entropy state. There are only so many movements those atoms or ions can make. They can vibrate slightly, but they can't take on, a huge number of ways of arranging themselves. A sodium will always be next to chlorides. And when I dissolve it, we can see that the entropy has increased because I have taken a molecule which is very rigid and structured, and I've allowed the ions in it to be able to diffuse and move around, and so I've increased the entropy. But I've also got kind of the bond energies taking place as well. So enthalpy, as you'll recall, is actually a measure of the entropy of the system. And so I have quite a lot of very strong bonds when I'm in this crystal lattice. But when I'm in solution, I still have bonding, because around every sodium ion and around every chloride ion, there is what we call a solvation shell. It is structured, ordered water. So around a sodium, we get the negative oxygen in water aligning itself towards that sodium. So the dipoles all arrange themselves with the oxygen in, and we get structure around that sodium. And the chloride aligns itself with the positive hydrogen atoms in the water. And that little dipole on the hydrogen atoms arrange themselves around the chloride. So we end up with this structure, and this affects the entropy that we see upon this dissolution step. The entropy is kind of more complex than just where the atoms are. So I've already said that we can relate it to the Gibbs equilibrium process, and if I can do that, I can get an equilibrium equation, and I have this KSP. KSP is my solubility product. It is my equilibrium constant for solubility, and I should always measure that in terms of the activity. So the activity of my products, and I don't have any reactants in this because my reactants are a solid, and the activity of them is 1. So I can forget those completely. So I have my activity of my products raised to their stoichiometric amount. Now, if something is sparingly soluble, in other words, if it doesn't dissolve very well, then I can replace activity with concentration. So our nomenclature is a little bit odd in terms of what we mean by solubility. So my solubility I've already introduced as this KSP, but my solubility tends to be the term that you see kind of out in the wild. Now, to a chemist, we would probably put the solubility as the number of moles of something we can dissolve, or more precisely, the concentration of that thing in solution when that solution is saturated. But for lay people, they also tend to use the mass. So how much mass can I dissolve in a litre or in a kilogram for a saturated solution? So solubility is in terms of essentially what is the concentration of my thing. So if I take something here, I've just got mx, but m and x are in the same stoichiometric ratio, and my solubility product is related to their activities raised to their stoichiometric amounts. And my solubility product is related to the concentration of that mx in the saturated solution, And so my concentration of my mx is going to be just my square root of my solubility product. If I take this to a slightly more complicated example though, and I have lead iodide, essentially the solubility of my lead iodide is going to be the concentration of the lead ions in solution, because it's 1 lead iodide goes to 1 lead ions. And here I've given you this example where I've got this equilibrium between lead iodide and its ions, and the solubility product of it is quite low at 8.49 times 10 to the minus 9. Now, because it's sparingly soluble, from this point on, I'm not using activity, I'm going to use concentration instead, because when it's something sparingly soluble, those two are interchangeable. And so my solubility product is the concentration of the lead 2 plus times the concentration of the iodide squared. But the concentration of my iodide is twice the concentration of my lead, so I can work that in and essentially get my solubility product of my lead iodide in terms of just one variable, which is my concentration of my lead. I can then rearrange that to work out the solubility. My solubility is the concentration of my lead solution, or my lead iodide in solution, and it would be 1.28 times 10 to the minus 3 molar in a saturated solution. Hope this concept bite has helped. Let me know if you need any more.